All right, number 11, determine whether this improper integral converges or diverges. If it converges, we're going to find its value. Again, we've got these e to the x's, just like we did on number 9. So we've got 3e to the x over 3 plus e to the 2x dx. We're trying to integrate that between minus infinity and infinity. In order to do this, we have to split it up into two separate integrals. Eventually, those two separate integrals are going to be translated into limits. That's how we handle improper integrals. I picked 0 to be that split point for the two different integrals, just because 0 is generally easy to work with. So the integral from minus infinity to infinity is equal to the integral from minus infinity to 0 plus the integral from 0 to infinity. That's a property that we have for all integrals. For continuous functions, we can split them up. Again, we've got these integrals, this integral that has some multiple expressions that are exponential, just like we did on number 9. We're going to go u substitution. We're going to let u equal e to the x. That means du is e to the x dx. E to the x dx in the numerator gets replaced with our du, and our denominator becomes 3 plus u squared. Again, e to the x squared is the same thing as e to the 2x, so that's why we can do that. So we're going to find the antiderivative first, then we'll go back and deal with the improper integrals. So, antiderivative of 3 over 3 plus u squared. This is reminiscent to me of the derivative of the arctan function. The derivative of arctan is 1 over 1 plus u squared. We don't quite have that. We've got that 3 kind of running around rampant in there. So let's get rid of that and see if we can kind of work with this and deal with an arctan. So 3 comes out of the denominator and I cancel it out with the 1 in the numerator. When we do that, now I've got 1 plus u squared over 3 there in the denominator. I want something 1 plus something squared in the bottom there, so that way it kind of works with the arctan derivative. So I rewrote it so it's 1 plus u over square root 3 squared. Again, from this step to this step is just a cosmetic change. There was nothing that happened there algebraically. I just said instead of writing u squared over 3, I'm writing it as u over square root 3 squared. That's it. Now I've got 1 over 1 plus something squared. So I know now for sure we've got an arctan in there. So what we've got is this is the derivative of arctan u over square root 3. If we want to have an over square root 3 in there, we need to undo that chain rule with the square root of 3 out in front. So the antiderivative of 1 over 1 plus u over square root 3 squared is square root 3 times u over square root 3. If you're not convinced of that yet, go ahead and do another substitution, maybe call it an a substitution and let a equal u over square root of 3, and then work with that, and then hopefully that'll be able to convince you. We don't want u's in here anymore. Okay, we want to make sure we undo that substitution. So our antiderivative is square root 3 times arctan, or tan inverse, e to the x over square root 3 plus c. We're not done yet. If you look up at the top of the page, our goal is to figure out if this integral from minus infinity to infinity is convergent. Finding that antiderivative was just the first step in that process. So let's kind of keep going. Again, we want to split that improper integral up. We're going to take the integral from minus infinity to 0. We're going to take the integral from 0 to infinity. We're going to replace those upper and lower limits of the integral and actually turn them into limit problems. So we're going to take the limit as a goes to minus infinity of the integral from a to 0. We're going to take the limit as b goes to infinity of 0 to b. We already have the antiderivative. That's what we did first. We figured out that antiderivative first. So we're going to make a substitution there with the antiderivative, so that way we can use the fundamental theorem of calculus. So now we've got the limit as a goes to minus infinity of the antiderivative square root 3 arctan e to the x over square root 3. We're going to evaluate that using the fundamental theorem from 0 to a, from a to 0. And then we're going to take the limit as b goes to infinity of square root 3 arctan e to the x over root 3, and we're going to evaluate that one at b and at 0. So when we do that, here's what happens. Square root 3 arctan of 0, e to the 0 over root 3 is pi over 6. So this is the first part. If if we then plug in a here, so square root of 3 arctan e to the a over 3, this quantity inside here is going to go to 0. E to the a is going to go to a very, very small number, so that's why that becomes 0. When b goes to infinity here, I'm going to have arctan of really, really big numbers. So I'm basically taking the limit as arctan goes to infinity, that's pi over 2. And then again, when we plug in 0 there, you can check that on your calculator. Arctan of e to the 0, that's 1 over square root 3, is pi over 6. So this guy cancels out with that guy 0, and we're left with pi times the square root of 3 over 2. So this integral converges, and it's equal to pi root 3 over 2. Double check here. Make sure you're convinced that this limit as a goes to minus infinity is 0. Initially, when I was kind of going through this quickly the first time, I was thinking, oh, it's arctan as a goes to minus infinity, so it has to be minus pi over 2. But it isn't, because we don't just have x or a inside that. We have e to the a, okay, as a goes to minus infinity, that's going to go to 0. So really what we've got here is arctan of 0, which is why that whole thing becomes 0. So we have another example of an improper integral that converges. The area under the curve, the entire length of the x-axis, and the area under the curve is pi times the square root of 3 over 2.